Bismillahirrahmanirrahim. In this video, we are going to briefly revise the modeling techniques for a control system. We can represent our system using the differential equations or state space model or using the transfer function. So consider this mechanical system. This is the spring and this is the damper. So if we apply the force u of t on this body of mass m, it will be displaced, and let's suppose that that displacement is y. So according to Newton's law, sum of all the forces should be equal to ma. So sum of all the forces must be equal to ma. The force that we are going to apply is u of t. This will be opposed by this spring force and by this damper force. So damper force is proportional to the velocity, so b into y dot will be the force that will be applied by the damper in the opposite direction of your applied force, and the spring force will be equal to k into y. So this is your applied force, this is the force because of the spring, this is the force because of the damper in the opposite direction, and sum of all these forces must be equal to ma. So from this equation we can write down the differential equation like this, right? So this a is basically equal to y double dot, right? So y double dot t plus by dot t plus ky of t, that must be equal to our input force. So we can write this equation like this, that m y double dot plus by dot plus ky, that is equal to u. So that is the differential equation representing this system. Now we can write it in terms of state space. So for that we will have to define the state space variables. So first of all, let's suppose that y is equal to x1, and if I take the derivative of this term y dot, so that will be equal to x1 dot, and let's suppose that is equal to x2. As the highest order of the derivative is 2, so two state variables will be required to represent this differential equation in terms of the state space. So from this equation I can write that y double dot is equal to x2 dot, right? So one first order equation can be written looking at this equation, that x dot is equal to x2. x1 and x2 are our state variables, and x1 dot is there, so it's a first order linear differential equation. So x1 dot will be equal to 0x1 x2 plus u. x1 is our state variable and x2 is also the state variable, u is the input, right? So we have this equation as the first order differential equation that will be representing this second order differential equation, and the second equation can be written taking this equation a. So from this equation I can write that y double dot is equal to minus k by m into y minus b by m into y dot plus u by m. So using the definition of the state variables x1 and x2 and x2 dot, I can write this equation like that, that y double dot is equal to x2 dot, y is equal to x1 and y dot is equal to x2. So we have this equation, that is x2 dot is equal to minus k by m into x1 minus b by m into x2 plus u by m, and this is the first order differential equation. So this equation 1 and equation 2 both can describe the system, this system, that is the second order differential equation in terms of the state space. So standard form of the state space equation is this one, x dot is equal to ax plus bu and y is equal to cx plus du. So we can write these two equations, this equation and this equation, in terms of the state space. So from the first equation, x1 dot is equal to 0 into 1, and from the second equation we can write it like that, minus k by m and minus b by m. So this is the x dot matrix, this is x matrix, this is the input matrix, right, this one. So in the first equation the input is 0, so that you can see over here the 0, and in the second equation the input is linked with the x2 dot by the factor 1 by m, so 1 by m into u. Okay, so this is our state matrix A, this one. This is our state matrix A, and the matrix B is this one, and the matrix C, the output matrix. That equation can be written looking at this one, equation A, this one, y is equal to x1. So output is defined as the defined by the state variable x1. So y is equal to over here, if we have the state variable matrix x1 and x2, so x1 is required at the output, so there will be 1 over here, and this will be with the 0. So y is equal to this matrix, that is consisting of 1 and 0 into x1 x2, those are the state variables. Okay, so plus d into u from here, but d in these two in these two equation is equal to 0. So this is 0, the D matrix over here. So matrix A for this system is this one, that is the state matrix, and the input matrix is this one, that is this, and this is the output matrix, and this is the direct transmission matrix, that is 0 in this case. Means our input is not directly linked with the output. Okay, now we have seen the differential equation defining this system, and then we have seen that how we can develop the state space model. Now moving towards the block diagram. So for the block diagram we have two state variables, x2 and x1. So let's suppose that y is equal to x1. So this is the integration, and over here will be x1 dot. If that is integrated, you will get x1. So what is this x1 dot? This is basically equal to x2, and that is equal to y dot, right? And how to get this one? An integrator over here whose input is x2 dot. So when it will be integrated, we will get x2 over here, and this x2 dot is equal to y double dot. So two integrators are required to get y from this y double dot, right? So therefore two state variables are there. Okay, basically we are implementing this equation. So x2 dot is equal to minus k by m into x1, then minus b by m into x2 plus u by m. So u is our input, this one. So it is scaled by this factor 1 by m and is given to this summing block, and this is basically implementing this portion, right? And the positive sign over here is this one. So with this term we are going to sum minus k by m into x1. So taking x1 from here, and the gain is k by m, that you can see over here. This is the gain, and this is given over here, and this negative sign is over here. That's why we do not need to add it over here. So the equation over here will be like that: u by m minus k by m into y, or k by m into x1, right? So this portion is implemented. Now to implement that one, we need to take x2. So this is x2, and this will be multiplied with b by m, and as it is the negative term over here, so it will go into the negative sign over here over this summing junction. Okay, so this is the block diagram representing the system that is being defined by these two equations. Okay, and finally the transfer function. The transfer function of this one can be easily written, and this is our differential equation. So taking the Laplace transformation of this one, you will get this equation, and then taking y as a common out. So then writing y by s by u of s, that's the ratio of the output Laplace with the input Laplace, so that comes out to be this one. So this is the transfer function of the system that is defined by this differential equation. Okay, now let's see that how we can represent, how we can determine the transfer function if the state space is given to us. So standard state space equation for a system is this one: x dot is equal to ax plus bu, and the output equation is this one: y is equal to cx plus du. So this is the output equation. So now if I consider this equation, state equation, so x dot is equal to ax plus bu, and if I take the Laplace transformation of this equation, so that is given by this one. So here we have the derivative. So the Laplace transformation is s into x of s minus the initial value of the function x of 0, and on this side it will be a into xs, and from here it is b into us. Okay, so assuming that initial value is 0, right? So with 0 initial condition, this equation can be written like that s into x of s, that is equal to a x of s plus b into u of s. So rearranging this equation, taking the input, that is taking the x term on one side, so I can write it like that: s minus a into x of s, and that will be equal to b into u of s. But remember one thing, that this is the matrix A, right? This is matrix A, so this must be in the form of the matrix. So I am going to write it like that: s into I, where I is the identity matrix, right? So why I am adding I over here? So that I can perform the matrix operation, because this A is the square matrix from the state space equation, right? So that's why I'm going to write it like that: Si minus A. So Si minus A into x of s, that should be equal to b into u of s. So now taking x of s over here, this term when will go to the other side, it will appear with the inverse. So Si minus A inverse into b into u of s will give me x of s. Okay, now taking the output equation is y is equal to cx plus du, and taking the Laplace transformation of this one, and then after Laplace transformation we can write this equation like this. Now if I take the value of this x of s from this equation and place it over here, so that you can see this is x of s. So I can write this equation, right? And rearranging this one and taking u of s common out from these two, so u of s is over here, so we will be left with this part. And transfer function, as you know, is the ratio of the output with the input. So y of s is the output and the u of s is the input in this equation. So y of s over u of s, that is the transfer function t of s or g of s, that will be equal to c into s into I minus a inverse into b plus d. So this expression defines that how we can get the transfer function if the matrix A, B, C and D are known. So the transfer function can be derived from the state space equation. For the sake of example, what we can do, we can consider the example that we have discussed over here, and we are going to consider these matrices A, B, C and D, and let's put them back in this equation that we have derived to determine the transfer function. So taking A, B, C and D matrices from that example, so let's see how we can develop the transfer function. So this was the system, this was a differential equation. We have written its state space model, and from this model we know the matrix A, B, C and D. Now we are going to translate it back into the transfer function. So what we can do, this matrix C is 1 into 0 and Si, so S into identity matrix, so you will get this one. The matrix A is this one coming from here into matrix B is this one, and the matrix D is this one. Okay, so as this matrix is 0, so this will disappear, so we have only this portion that is to be evaluated. Now combining these two matrices, S minus 0, S 0 minus 1, so this will become minus 1, 0 minus k by m, so we will get k by m, and then S minus and minus plus, so S plus b by m into this 0 and 1 by m matrix. Okay, so we need to take the inverse of this matrix. So the inverse will be equal to 1 by determinant. So in order to take the determinant, what we will have to do, sorry, over here it will be minus 1. So this should be minus 1. Okay, so now to take the determinant, s into s plus bm, so this will become s square plus sbm, and then minus the product of these one, so minus minus plus, so this will become k by m. So this is the determinant of this matrix, and then the adjoint is obtained by changing the position of these two and then changing the sign of these two terms. So this is the adjoint of that one. So this is the inverse of this matrix. So now using this inverse over here, this is this term, and this matrix from here, and this one from here, and this one from here. Okay, so now if we multiply these two matrices, we are going to get this one, and then if we multiply these two matrices, this is of order 1 cross 2 and this is of 2 cross 1, so the resultant is 1 cross 1, so that is 1 by m. So 1 by m divided by this part. So now simplifying this one, we are going to get this equation, and this is exactly what we derived earlier directly from the differential equation, right? So we derive this one. So we can derive the transfer function from the state space. If the matrices A, B, C and D are known to us, we can easily derive the transfer function. Okay, now let's look at the example, and that example will help us to understand that how we can develop the how we can develop the state space directly from the block diagram. So this block diagram is given to us, and what I have done, I am going to consider that this is x1s, this is x2s. X2s is being given to this transfer function as an input, and the output is x1s, right? So first of all, considering this portion of this block diagram, so from here I can write that x1 of s divided by x2s, that will be equal to 10 by s plus 5. That's the transfer function between these 2 points, and from this equation I can write, if I do the cross multiplication, and I simplify, I can write it s into x1s, that will be equal to minus 5 into x1s plus 10 into x2s, right? So I can write the equation like this, and I am taking s over here. Why? Because s represent basically the derivative. So this is basically like that in time domain. It can be written as x1 dot, right? So this is basically the first order linear differential equation in s domain. So this is the transfer function between these 2 points. Now I'm going to consider this point and this point. So output is x2 of s, and the input over here is u minus x3s. So x2s divided by u minus x3s, that should be equal to the transfer function. The transfer function in between is this one, 1 by s. 1 by s is simply the integrator, right? So this is the equation, this is the transfer function between these 2 points, and then rearranging this one, I can write this equation. Okay, now taking this portion, x3 is the output of this transfer function block, and the input is x1s. So I can write in terms of the transfer function like that, x3 by x1s, that is equal to 1 by s plus 1, and again simplifying this equation, so it will be represented like this. Okay, and what is the output? Output is x1 of s. So the output equation can be written like this. Okay, so from this block diagram, I have considered these 3 points, and this is the integrator, this is also the integrator, but some gain and this frequency over here. Okay, so this summing block, the input is u of s, so x3 is coming from here, so the output is u minus x3s. That's why we have reflected that one in this transfer function. Okay, now from these 3 equations, we can write that x1 dot is equal to minus 5x1 plus 10x2, and x3 is not present in this one, so it is with 0, and no input is linked, so 0 in u, And now taking this equation, x2 dot 0x1 0x2 minus x3, and the input is linked directly. And then from this equation I can write x3 dot, that is equal to x1 plus 0x2 minus x3 plus 0u. And now we can write it in terms of the state space. So we can get the state matrix from here: minus 5, 10, 0, 0, 0, minus 1, 1, 0, and minus 1. And the input is only linked in the x2, right? So the input matrix will be written like that: 0, 1, and 0. And the output is linked only with the x1, so output equation for the x1 we will be having 1, and for x2 and x3 we will be having the 0. And the direct transmission matrix, that is D, that is 0. The input is not directly linked with the output. So this represents the state space of this block diagram. So by defining the state variables over the block diagram, you can write down the state space representation of the system. So that's all from this video. If I conclude, we have discussed that how we can develop the transfer function from the state space, and we have derived the expression for that one, and we have seen an example at how we can develop the state space directly from the block diagram. Thank you very much.